Okay guys, let's try this the third time. So I got everyone's phones off the Wi-Fi, I restarted my computer, hopefully this will work, and turned off my kids' movie. Okay. So we're trying to look at L'Hopital's rule, and L'Hopital's rule again is analyzing what happens in these weird cases such as 0 over 0, infinity over infinity, and way back in Calculus 1 when we're looking at limits and we end up with something 0 over 0, most of the time we could use some sort of algebra to get around the problem, okay? And but in this example here, ln x over x minus 1, where I get 0 over 0 at the value 1, algebra, I mean, there's not really much I can do, okay? So that's where L'Hopital's rule comes into play. Bear with me. We're going to, let me just write out what it's saying, and then we will do some examples, okay? So first we need two functions. Let's suppose f and g are, well, we need them to be differentiable, and we also need we need that the denominator not be 0, okay? So f and g are differentiable, and I said the denominator, that's not exactly what I meant. I meant the denominator's derivative on some interval. Typically we write this a to b, but when you get into higher mathematics you just say something like this, some interval I, and with some value a being in that interval, okay? Now suppose that also when we get the limit of x approaches a of f of x over g of x, we get either 0 over 0, or when I take this limit, I get infinity over infinity. And these things should cringe when you write this out because these are not defined statements, right? Infinity over infinity is not something we know, but we're just using this as a way to denote what's going on. What I mean by this is that the limit is x approaches a of f of x is going to infinity, and the limit is x approaches a of g of x is going to infinity. So these are the two cases that we're looking at first of all. So let's write that up here. We have 0 over 0, infinity over infinity. Those are two of our indeterminate forms that this version of L'Hopital's rule addresses. Here's what's weird. Alright, so we have suppose all that. Then we can say then, or let's say period, capital T, then the limit as x approaches a, I wrote infinity here, but I meant a, of f of x over g of x is the same as the limit as x approaches a of, and this is exactly what Cal 1 students want to do a lot. If they're trying to do like quotient rule, just the derivative of the numerator over the derivative of the denominator, we get f prime x over g prime x. Okay, so in here we gotta say if this limit exists, or 0. If this limit exists, or is 0. In other words, let's not run into another indeterminate form. Okay, so that's a lot of wording, but think about what we're saying here. We're saying that, look, if you have this indeterminate form 0 over 0, infinity over infinity, then what you can actually do is just take the derivative of the numerator and the derivative of the denominator and look at that limit. And then that would be a limit that we could evaluate, possibly. All right, so we're going to look at some examples. Maybe the one we should look at is the one that we first came up with. So let's go back to look at the limit. We'll call this example 1. Let's find the limit as x approaches 1 of that ln x over x minus 1. Okay, so first of all, is ln x, or the functions ln x and x minus 1 differentiable? Yes, anywhere. I mean, they're fine on their domains, okay? And So are we allowed to use L'Hopital's rule? Well, first you got to check, is it an indeterminate form? So notice that we already covered this, but when x approaches 1, ln 1 is 0, and x minus 1 is obviously 0. So we have a 0 over 0 form. That means we can use L'Hopital's rule, which I'll denote L apostrophe H. I think that's clear enough. And so from that we can say then all we need to do to evaluate this limit, so the limit as x approaches 1 of ln x over x minus 1 equals, according to L'Hopital's rule, the limit as x approaches 1 of, let's take some derivatives. So the derivative of ln x is 1 over x. Got it? Okay. And the derivative of x minus 1 is 1. So by L'Hopital's rule, this is the same as saying the limit as x approaches 1 of 1 over x. Okay, and since 1 is in the domain of this function and it's continuous at 1, we can just plug 1 in, get 1 over 1, or just simply 1. And there is our solution. So does 0 over 0 equal 1? Well, I'm not going to say all the time, but here it does. Okay, and I hope that makes sense. Now, L'Hopital's rule is a very powerful tool, but I have a lot of students, or students in the past, have tried to apply it where they're not allowed to apply it. And so that's why we took the time to write all this down. You have to have these forms, 0 over 0, infinity over infinity. And it's also worth checking if we're differentiable, etc. And if you're not in a higher math course like something like advanced calculus or real analysis, most of the time we don't trick you with that kind of stuff. In upper math, you do have to worry about that. Alright, so let's look at example 2. This time we want to find the limit as x approaches infinity of e to the x over x squared. And I'm seeing I'm getting some bit rate problems again. Hopefully it's not too big of a deal. Just let me know if it becomes an issue, okay? I might just have to keep going because there's not really a lot I can do at this point. Okay, so let's look again at this limit and let's figure out what's going on. So as x goes to infinity, what happens to e to the x? Alright, so let's do that first. The limit as x approaches infinity of e to the x. Well, we know that that graph's just going to blow up, so this goes to infinity. And the limit as x approaches x squared, well, we know the parabola, the end behavior as x approaches infinity is also infinity. So from that, we derive that this is an infinity over infinity situation, and which is actually good for us because that means we can use L'Hopital's rule. All right, and if we didn't have L'Hopital's rule, or if we didn't have infinity over infinity here, this might be pretty tricky. Okay, so let's then take the derivative. We're going to say the limit as x approaches infinity of e to the x over x squared equals, by L'Hopital's rule, I'll change color just to show that we are applying that. The derivative of e to the x, which funny enough is e to the x. So we have e to the x, that's the derivative of e to the x. In the denominator, we have the derivative of x squared, which is 2x, right? Okay, but notice here that when I evaluate this going to infinity, again, I end up with an infinity over infinity situation. Because the limit is x goes infinity of 2x, well, that's a straight line, and it's going to go up to infinity as well, right? So we didn't really evaluate the limit, but we can apply L'Hopital's rule again. So let me change my color one more time. So we are going to apply L'Hopital's rule one more time. And again, the derivative of e to the x is simply e to the x. And then the derivative of 2x is just 2. So now I basically just have a multiple of e to the x. And so 1/2 e to the x as x goes to infinity, we get infinity. And there's my limit. We've found the limit. So the limit as x approaches infinity of that thing is infinity. Okay, now we might have been able to reason this out at the beginning, because if you think e to the x is exponential, that's growing a lot faster than x squared. And so because of that, the numerator, as x approaches infinity, the numerator of this function is kind of taking over. It's the one that's dictating what's happening. So from that, I could have reasoned out in my head that this is going to go to infinity, but reasoning out in my head is not really the mathematical approach, is it? We have to be able to communicate precisely why it's doing this, and L'Hopital's rule helps us figure that out. So for your notes, we applied L'Hopital's rule right here, and we applied L'Hopital's rule right there. Okay, so we applied L'Hopital's rule twice in this situation. Good, I hope that makes sense. All right, now what we want to do for the rest of our time is just kind of look at different examples of this. There are some tricks involved. You can't always directly get it into one of these indeterminate forms, 0 over 0, infinity over infinity. But let's just see what we have. Okay, so we'll do some examples of both. We'll kind of mix it up. So example 3, I want to find the limit as x approaches infinity of ln x over the cube root of x. Okay, now both of these, ln x, even though it grows kind of slowly, it goes out to infinity as x approaches infinity. Okay, so ln does not have a horizontal asymptote. The cube root of x, same deal. It does not have a horizontal asymptote as either. And so we get an infinity over infinity situation, which means I'm allowed to apply L'Hopital's rule. And so we can say then that this limit, the limit as x approaches infinity of ln x over the cube root of x, is going to be, okay, we're going to have to do some thinking here. The limit as x approaches infinity of the derivative of ln x, the derivative of ln x is 1 over x. And then the derivative of the cube root of x, which is hard until we realize that that's the same thing as x to the 1/3 power. Right, so x to the 1/3 power is the cube root of x. So its derivative is going to be 1/3 x to the what power? 1/3 minus 1, which gives me the negative 2/3 power. Okay, now I just have to simplify this, and the way you do that is by remembering dividing by a fraction is the same as multiplying by its reciprocal. Okay, so this 1/3 is actually 3, and what about the power? So let's clean this up a little bit before we try to evaluate this. So that's going to be the limit as x approaches infinity. Let's see, this is 1 over x, and in the denominator we have 1 over 3 x to the 2/3 power, right? Because the negative means reciprocal. So that's actually all we have in the denominator, which means then that if I dividing by a fraction is the same as multiplying its reciprocal. This is the same thing as saying 1 over x times 3x to the 2/3 power, leaving me with 3x to the 2/3 power over x. And then now I can pull that negative 2/3 down into the denominator again. And let's see if this makes sense to you. That's going to be 3 over x to the 1/3 power, right? Because this is x to the first, that's x to the negative 2/3. When you multiply, you're adding the exponents. We get positive 1/3. Okay, and now I think we're allowed to evaluate what happens to this function as x goes to infinity. The 3 is a constant, doesn't do anything. The x to the 1/3 power goes to infinity, so 3 over something approaching infinity gives me 0. And there is my solution. So this time, infinity over infinity actually didn't equal 1 or something like that, or infinity, it actually equals 0. Okay, so if someone asks you, hey, What's 0 over 0? 0 divided by 0, or infinity divided by infinity? Well, you could say it just depends on the context. Depends on how you got there, right? Because infinity over infinity is not a number. It's just a symbolic expression of a limit where the numerator and the denominator are simultaneously approaching infinity. But the ratio of those two things could go to infinity, could go to something finite, right? And so, yeah, so we have to be careful in what we're saying here. We're being kind of loose with our wording just because it's a little fun. Okay, let's try another one. If you have questions, please let me know. So example 4, I want to find the limit as x approaches 0 of tan x minus x all over x cubed. Tangent x minus x all over x cubed going to 0. Okay, now, what kind of situation is this? Hopefully this is something we can apply L'Hopital's rule with. So let's think. Well, the denominator is definitely 0, right? X cubed as x approaches 0 is 0. How about the numerator? Tangent of 0 is 0, and 0 minus 0, we get 0. So again, we are allowed to directly apply L'Hopital's rule to evaluate this limit, and that's our only shot at evaluating this, unless we try to do some sort of graph approach. But that, again, that's not exactly precise. So we're looking at the limit as x approaches 0, tan x minus x over x cubed. And so now I got to take the derivative of the numerator and the denominator. I'm allowed to do that because of L'Hopital's rule. So I'm going to put a note here. I'm doing L'Hopital's rule right here. And the derivative of tan x is what? Secant squared. Very good. The derivative of x is 1. And in the denominator, we get 3x squared. Now, I want to point out again, this is what first semester calculus students want to do when we start doing quotient rule, right? They want to take the derivative of the numerator and the denominator, which is completely incorrect. And it just takes practice understanding you have to use quotient rule. Now, in this context, though, we have to kind of undo what we've learned. We're not doing quotient rule here. I'm not trying to take the derivative of the function tan x minus x all over x cubed. If I'm treating that as one function and I'm trying to take its derivative, I have to use quotient rule. I'm not doing that here, though. I'm just simply trying to evaluate the rate of change of the numerator divided by the rate of change of the denominator. And in these indeterminate forms, that actually is the same as the rate of change of the numerator over the denominator, or the evaluating where the limit is going. Okay, so here again, I took the derivative of the numerator and then the denominator because of L'Hopital's rule, and hopefully I can evaluate this. But if you remember, what happens to cosine at 0? Cosine of 0 is 1, so secant at 0 is 1, so secant squared is 1. My numerator, I get 0 over 0, or I'm sorry, my numerator I get 0 again. And you can see in my denominator, I'm going to get 0 over 0. So here, I'm going to have to use L'Hopital's rule a second time. Okay, so in doing that, let's see. I'm trying to find a good color here. And I'm going to apply L'Hopital's rule. Now, here in my numerator, I'm going to have to use chain rule, right? Because the derivative of secant squared x is going to be 2 secant x times the derivative of what was inside of that, which is secant. And then the derivative of 1 is 0. Okay, so I just have 2 secant x times secant x tangent x over the derivative of the numerator, which is 6x. Okay, so cleaning this up a little bit, let's see, I end up with secant squared tan x over the 2 and the 6 can cancel out to give me a 3x in the denominator, like that. Okay, from there, what am I allowed to do? Okay, so I'm going to pull this apart a little bit, and I end up with 1/3 the limit as x approaches 0 of secant squared, okay, times the limit as x approaches 0 of tan x over x. Now, this is, if you remember, if you have to go back and look at Cal 1, how we can pull apart limits like this, feel free to do so, but we're allowed to break up over products. And the limit is secant x squared. I mean, we already thought about that earlier. Cosine at 0 is 1, therefore it's reciprocal, which is secant is 1 at 0, so secant squared is also 1. This is 1 right here, okay? So then I just end up with the limit as x approaches 0 of, well, I could take out, let's take out the 1/3 first. 1/3, the limit as x approaches 0 of tan x over x. Okay, now what is happening to tan x over x as x goes to 0? Well, are you kidding me? Tangent at 0 is 0, x is 0 at 0. We have a 0 over 0 situation again. So for the third time, we're going to use L'Hopital's rule. Okay, now, what's good about this example is that it reminded me that once I got here, I looked like I was stuck. I mean, I might have to keep taking derivatives. This thing's going to get uglier and uglier. But I remembered I can pull apart these two limits to get this expression we have down here. And then the limit of secant squared is 1, so it simplifies what I'm actually trying to do, okay? All right, so now I'm going to apply L'Hopital's rule again. And when I do that, I have 1/3 the limit as x approaches 0, the derivative of tangent, which is secant squared, and the derivative of x, which is just 1. So I end up with secant squared over 1. We already evaluated the limit as x approaches 0 secant squared, right? It's 1. So I just end up with 1/3. So what is 0 over 0? 0 over 0 is 1/3, depending on your context. Okay, Courtney asks, what's the overall goal of these problems? And so what you have to remember, the limit, what are we talking about with a limit? We have some sort of function. So in particular with this one, if you graphed it, you would get something kind of like this. All right, and my graph's not great, but you're trying to figure out, so here at 0, what is the trend? If I'm going this way and I'm going this way, how is this graph behaving in the y direction, in the f of x direction? And so what we're saying here is as x approaches 0, this function actually trends to the value of 1/3. Okay, now with the graph, we might be able to point that out, but it's not precise. We have to verify it through our calculus. And so the calculus here, we end up with a 0 over 0 form. 0 over 0, we have no idea what that means, okay? And so L'Hopital's rule helps us. It's the only way we can simplify these things because here algebra doesn't work. So what I mean by that is think back to Cal 1. So here's a Cal 1 example. We might say something like this. The limit as x approaches 1 of, let me think real quick. We'll put x minus 1 in the denominator, so that gives me a 0. In the numerator, let's do x squared minus 2 here, and then minus x in the middle. Okay, so we have this function, and we want to evaluate as x approaches 1. Well, notice here, if I plug in 0, 1, no, I meant to make that a plus. So if I plug in 1, I get 0 in the numerator and a 0 in the denominator. So what we said is, hey, use some algebra. And the reason is because I could factor my numerator as x minus 1 times x plus 2. Hopefully I did that correctly. And my denominator of an x minus 1. And now I can cancel some stuff out and end up with the limit as x approaches 1 of x plus 2, which is something I'm allowed to plug in because it's continuous, and just get the value 3. Okay, so that's how we did it in Cal 1. But the truth is, using algebra to simplify these things only happens very rarely, right? It only happens, 1, when we're dealing with polynomials, and then 2, when we can deal with polynomials that we can actually factor. So here, we need a more powerful technique, and that's what L'Hopital's rule does. When we can't use algebra and we have these indeterminate forms, L'Hopital's rule will help us get there. Okay, good. I hope this makes sense. All right, let's look to another example here. Okay, now, I was wondering about skipping the next example, but let's go ahead and look at it. Example 5, because I want to point out something. This is pretty neat. So let's approach pi from the left, sine x over 1 minus cosine x. Now, you have homework on this, so you're thinking, okay, this is section 6.8, so I just need to apply L'Hopital's rule. And if I apply L'Hopital's rule here, watch what happens. So I get the limit as x approaches pi from the left of the derivative. We get cosine x in the numerator. We get the derivative of the denominator would be positive sine x. So I get tangent x approaching pi from the left side. We end up going to negative infinity. Tangent's got an asymptote there at pi, and from the left side, it's tanking down, or going to the left, it's tanking down to infinity, like this. So here's pi, and approaching from the left, I said, yeah, it's going to do something like this. Right? Okay. So, what do we do? Well, this is actually not correct. And why is it not correct? It's not correct because I didn't need to apply L'Hopital's rule in the beginning. This is not indeterminate. Okay, so I didn't have a 0 over 0 situation to begin with, or an infinity over infinity situation. So we need to be careful. Don't just pull the trigger immediately. So if, well, actually, I'm sorry. Let me think. Do we get a 0 over 0? We do, don't we? Sine of pi is 0. And cosine is going to be negative 1. Or, sorry, positive 1. No, it's not. It's not. Okay, I'm sorry. My coffee hasn't kicked in quite yet. All right, so let's look at this again. If I'm evaluating this, do I get a 0 over 0 situation? I thought I did at first, but actually I don't. Look, well, we can evaluate it directly. Sine at pi is 0. Cosine is negative 1 at 0. So I get 1 minus a negative 1. 0 over 2, which is simply 0. It was never indeterminate in the first place. So why would I apply L'Hopital's rule? You can only do that when you get 0 over 0, okay? Sorry I tripped over that. I was kind of confused myself because I was looking for the 0 over 0, and of course it's not there. Okay, now, hopefully this is making sense to you guys. Let me show you a few ways where you can kind of get around. Well, you have an indeterminate form, but you may not recognize it at first, okay? And so we're going to have to use some new techniques. So let's call this indeterminate products. Okay, so what would that mean? Like 0 times infinity. What's 0 times infinity? Well, I don't know. Okay, so here, example 6, we want to evaluate. So find the limit as x approaches 0 from the right of x ln x. Okay, now remember, what happens at infinity? I'm sorry, what happens for ln x as you get close to 0. You're going to dip down to negative infinity. So here I have a 0 times a negative infinity situation. What is that? What is 0 times negative infinity? I don't know. Can I apply L'Hopital's rule to it? No, you can't. So what can I do? Well, let's do some manipulation here. Let's let x approaches 0 from the right watch this. I'm going to say, instead of saying x, I'm going to use the fact that dividing by x is the same as multiplying by its reciprocal. So I'm going to have ln x over, instead of x, I'm going to divide by 1 over x, like that, okay? And so that is the same thing as x ln x. Dividing by 1 over x is the same as multiplying by x. And what happens now, as x approaches 0, in the numerator here, I'm just checking, let's see, in the numerator, we know we go to negative infinity. In the denominator, well, I'm going to, coming from 0 from the right, I'm going to infinity. This is an indeterminate form, so I can use L'Hopital's rule here. All right, so we're going to use L'Hopital's rule. And so this manipulation here allowed me to get into one of the forms that I knew already. And I have the limit as x approaches 0 from the right of ln x is 1 over x. Of 1 over x, I get what? Negative 1 over x squared, right? Because it's the same as x to the negative 1 power. And now I can do some algebra on this, I think. Let x approach 0 from the right. Dividing by fraction, same as multiplying by reciprocal. We end up with negative x squared over x, which is going to be just negative x. And so approaching 0, we just get the value 0. Does that make sense? I hope so. So now what's happening to the function x ln x as I get close to 0? I mean, we're trying to just learn the behavior of these weird functions. Well, at first it's not exactly clear. I mean, x is going to 0 for sure, but ln x is going to negative infinity. What dictates what? Well, we see then actually is going to go to 0. Okay, let's try another one. So I want to show you differences, indeterminate differences. So in other words, what is infinity minus infinity? What is infinity minus infinity? Okay, well that doesn't really, I mean, is it 0? Maybe, maybe not. Alright, so let's look at an example. Example 8. If you have any questions, please let me know, okay? I want to make sure we feel good about it. This can be a little bit of a tricky situation, or tricky section, because it's just something we're not used to thinking about. But again, all you're trying to do is look at the trend of these weird functions at a given point. And even though they come up with something that's nonsensical, like what we're about to see, infinity minus infinity, realize that we have a way to look at that trend through the derivatives. All right, so here we're trying to find the limit as x approaches pi over 2 from the left of secant x minus tangent x. Okay, so we have secant x minus tangent x approaching from pi over 2. All right, now let's think. Okay, so if we did some graphing here, remember cosine is 0 at pi over 2, so it's reciprocal, which is secant. Well, I mean 1 over 0, what's going on? We have to think about that the limit as x approaches pi over 2 from the left of secant x. We could look at the graph and see that it has an asymptote, and from the left side it's going to approach positive infinity. And tangent, I mean, again, since tangent is secant over, sine over cosine, we still have a problem because the denominator is 0 at pi over 2. So tangent, what's happening from the left side as you're going to pi over 2 from the left, we also go to infinity. And so for that reason, we end up with a infinity minus infinity situation. Can we use L'Hopital's rule? We can, but not yet. Okay, so not quite yet. We need to be able to massage this a little bit to get it in the right form, just like the previous example. Okay, so how can we do that? And I've already referenced the way we're going to do this is by thinking in terms of cosine, sine and cosine. So secant is the same thing as 1 over cosine, and tangent is the same thing as sine over cosine. So you need to get some sort of denominator involved. If you have an infinity minus infinity, figure out a way to put in a denominator to bring them together so they can go from, because we don't know about subtraction, but maybe if we get them on top of each other, we can turn it into another one of L'Hopital's forms. And I think that's what we're going to do here. Let's see. So as I approach pi over 2 from the left, and I bring these together, I get 1 minus sine x over cosine x. Okay. We know that cosine x is going to be 0, so the denominator is definitely 0. The numerator, sine of pi over 2, is 1, so this ends up being a 0 over 0 situation again. Now we can use L'Hopital's rule. Okay, so I'm going to use L'Hopital's rule and take the derivative of both sides. I mean, the numerator and the denominator. I wrote prime. I'm approaching pi over 2 from the left. The derivative of cosine is what? Negative sine x. The derivative of sine is cosine, so I get 1 minus cosine x. Okay, and, I'm sorry, the derivative of 1 is 0, right? So here, cosine x at pi over 2 is 0, sine of x is 1, so it would be negative 1, but it doesn't matter. We end up with 0 as my solution. I hope that makes sense. So the first thing, when you're looking at this, the first thing you need to do, first of all, is get comfortable with these early examples when you have 0 over 0, infinity over infinity. Just get comfortable taking the derivatives of the numerator and the denominator and evaluating from there. If you need to go back and learn some of your limit rules, completely understand, it makes sense, okay? From there, we start looking at like products, 0 times infinity, what's going on. You have to massage it somehow to get it back into one of our traditional forms. Same with indeterminate differences, infinity minus infinity. You have to do some sort of manipulation to get it back into one of our earlier forms that we were dealing with. And the same with this last category. Okay, so here we have indeterminate powers. Indeterminate powers. And so what kind of things are we talking about? We could have something like this. 0 to the 0 power. Well, okay, hold on. 0 to any power, 0 to the 5th power, for example, is 0. Also, though, anything to the 0th power is 1, right? Like 6 to the 0 power is 1, 1,000 to the 0 power is 1. What about 0 to the 0 power? I don't know. What about infinity to the 0 power? I mean, anything to the 0 power is 1. So infinity to the 0 power, I don't know, it's indeterminate. And how about this one? 1 to the infinity power. So 1 to any power is 1, right? 1 to the 17th power is 1. But let's let the power go to infinity. 1 to the infinitieth power. I don't know. I don't know what that is. Okay, so these are all cases in which we're going to have to use L'Hopital's rule. And we're going to have to be a little creative in how we do it. And most of the time, I mean, when you have a variable exponent, what do you look to? You need to look to logarithms, and that's exactly right. So, for example, example 9. This time we want to find the limit as x approaches 0 from the right of 1 plus sine 4x raised to the cotangent power. Are you kidding me? Okay, so this is, think about it, as I'm approaching 0, sine of 0 is going to be 0. So this is going to be 1 raised to, you may not know exactly what's happening with cotangent at 0, but think tangent at 0 is 0. So cotangent at 0 is going to have an asymptote, which is either going to go to positive or negative infinity, and it will go to positive infinity. So this is definitely an indeterminate form. I'm going to try to use L'Hopital's rule, but I got to get it into a situation, a place where I can use L'Hopital's rule first. And the way we're going to do that, again, since I have that cotangent x power, I'm going to use the logarithm. So I'm going to let y be 1 plus sine fourth x to the cotangent x power. So then I'm going to use ln y to take, or I'm taking the ln of both sides. And the reason that's useful is because now I can say that this is cotangent x, oops, I wrote y, but cotangent x times ln 1 plus sine 4x, like that. And here we have ln y, okay? Now what I want to do is let's look at the limit. Let's look at the limit as x approaches 0 from the right of ln y. Okay, so we're taking the limit, that limit that we wanted on both sides here. And I'm going to do something kind of clever. I remember that cotangent is 1 over tangent. So I'm going to have the limit as ln, the limit as x approaches 0 from the right of ln 1 plus sine 4x over cotangent x. Okay, now I believe I have an indeterminate form. So let's think about it. Do I? As x approaches 0, I get, in the numerator I have 1 plus, or ln of 1 plus 0. Ln of 1 is 0. So in the numerator I have 0. And, oops, and I wrote cotangent. I meant tangent down here in the denominator. Tangent x is 0 at 0. So there I have a 0 over 0 form. And now I can use L'Hopital's rule. Alright, so we take the derivative of the numerator and the denominator. It's going to look a little ugly. That's okay. You want to start with the denominator. The denominator, the derivative of tangent is secant squared. The derivative of the numerator is going to be 1, well, you have to use chain rule, right? So how do you take the derivative of ln u? It's 1 over u times du. So the 1 over u, that's going to be in the denominator here, 1 plus sine 4x. And the numerator is going to be that derivative. The derivative of 1 plus sine 4x is cosine 4x times the derivative of what's inside of that, so times 4. And that is chain rule that we had to use there. And I'll just denote here, that's the numerator, and that's the derivative of the denominator, because it can be kind of confusing. But here, I think from this point, we can just directly evaluate what we have here. Even though it's ugly, let's think. The denominator, secant squared, we know, we've already talked about that twice. The limit as x approaches 0 of secant squared is going to be 1. So that's a 1 down here in the denominator. In the numerator, let's see, cosine at 0 is 1. So the numerator of the numerator is 4. And the denominator of the numerator, what happens to sine at 0? That's 0. We have 1 plus 0. And so if you think about this, then that's just going to be 4 over 1 divided by 1. We end up with 4. And there's my answer. Well, not quite. That's not quite my answer. Because we have, thus, the limit as x approaches 0 of ln y equals 4. Okay. That's not exactly what we wanted, right? We wanted the ln as x approaches 0 on the right of y. Okay. But remember, that's the same thing as saying e to the ln y power, right? Because we can, e and ln are going to cancel each other out. And so we have this funny way of writing any number is e to the ln of that power is actually the same thing. And we know what's happening as x approaches 0. We know what happens to ln y. Ln y is going to approach 4. So this numerator, the exponent, is actually approaching 4. So my final answer is e to the 4th power, which is not, what were we starting out with? 1 to the infinitieth power, and we got e to the 4th. That's odd. But again, it's because 1 to the infinitieth power doesn't mean 1 times itself an infinite number of times. It's what is the trend going? What is the trend happening when you end up with a situation like that? Like this we had in example 9. Okay? And again, the trick, just like the other two tricks, is we had to figure out a way to get it to a traditional L'Hopital rule form. And the way we did that was through this taking the ln of both sides idea. And that helps me pull the exponent out. Okay? Let's finish with one more, because I just think these are so cool. I hope you have, if you have questions, I'm sure you do, just let me know. Okay? I'd be glad to help. All right, example 10, and this will be our last one here. We're going to find the limit as x approaches 0 from the right of x to the x power. X to the x power. And this is a 0 to the 0th power situation. So is it 1? Well, maybe. And even if we do get 1, you can't just go around saying 0 to the 0th power is 1. It just depends on the context. Okay, it depends on the context. All right, so again, what we're going to do is the same idea. We're going to let y equal this x to the x power. Okay? And when I take the ln of both sides, I can get x ln x. So now what I'm doing is I'm evaluating the limit as x approaches 0 from the right of ln y, which is x approaches 0 from the right of x ln x. And that looks tricky, but we already did that one, right? This is my example 6. Okay, so we knew how to do that, right? You take the x and rewrite it as 1 over x. Then you can apply L'Hopital's rule, and what we got way back when we did that example was 0. Okay, so what we know then is that the limit as x approaches 0 from the right of ln y gives me 0. So what I really wanted, though, remember, was this was y, which is x to the x power, is going to be the limit. We're applying the same trick we did last time. Remember, if you have y, you could rewrite that as e to the ln y power. Okay, and what was ln y? X ln x. Okay, so here, if you're trying to visualize it, this is y, and this is e to the ln y power. Okay, and we know what's happening to that numerator. The exponent. We know that this exponent approaches 0. That's what we did in example 6. So this is going to end up being e to the 0 power, which is, oh, come on, really? 0 to the 0 power, in this case, was 1. It won't always be 1. It just depends on the context. Okay. L'Hopital's rule is a little odd, and it's kind of weird, and you may be wondering, why is it stuck in here with the derivatives of ln and e to the x? For this very reason, so that we can finally look at all the different cases of that require L'Hopital's rule. All right, it's a very valuable tool to have. It's one you need to put in your back pocket. It'll show up from time to time in unexpected ways, and it's really just incredible to think about. Guys, if you have any questions on this, please let me know. I'd be glad to help. I hope you're doing well, staying safe, being smart. Just keep studying, keep working hard. We care about you. Let me know how I can help you again. And thanks for watching, guys. Have a good weekend.